Across businesses, teams within different domains are struggling to solve the same core problem. For teams analysing fraud and financial crime, increased sophistication means it's becoming harder to spot malicious attackers amid costly regulations. Insider threat specialists are trying to find potential perpetrators amidst a sea of activity data from an ever-expanding list of sources and software applications. And IT teams are attempting to make sense of visibility into modern apps formed of 1,000 plus microservices, any of which could be causing a platform issue. And these are costly problems too, whether it's fraud where the total annual cost is estimated to be 3.7 trillion a year globally, insider threat which on average costs businesses over $15 million an incident, or downtime which has an estimated impact of $9,000 a minute. Customers all want to know the answer to one simple question. How can I see when something is behaving normally or abnormally? This could be the difference between a user and the wider user base, a service and its past behaviour, or any other thing in a group of things represented in your data. So why has this question been hard to answer in the past? Well, what's like to happen when you start trying to implement a solution to a behavioural use case? You're going to hit a number of challenges, and the first of those is just sheer complexity. Choosing the right methodology or approach for anomaly detection is hard. Implementing an anomaly detection method in Splunk and Splunk's search processing language can be hard. And monitoring, maintaining and ensuring that everything you deploy continues to work is hard. Then there's the scale. The number of entities for some of these use cases can be enormous. When looking to profile external customers or IP addresses, we're talking about maybe millions of individual entities, not just thousands or tens of thousands like you might find in a typical security or IT ops use case. We're also potentially going to want to make many different anomaly detections across lots of different entities, indicators and signals. And then there's the noise. Most, if not all, methodologies for anomaly detection are inherently noisy. You're very unlikely to have a single anomaly detection trigger only on the events you're interested in without also getting a lot of false positives. And this is doubly true if you're dealing with large numbers of entities, as some are always bound to look different. The only way to deal with this is to implement a system of anomaly detections, and all of the workflow around this needs to be implemented. Whether that's data cleanup and normalization in the beginning, aggregation of multiple noisy outputs together to form high value events related to specific entities, or managing, monitoring, updating and adjusting searches to optimize score outputs over time. And all of this is where the Splunk app for behavioral profiling comes in. So let's say we're a fraud analyst tasked with identifying potentially fraudulent users on our payments platform. Now, in the past, we would have had to learn Splunk's search processing language and potentially some machine learning algorithms, build a search, schedule the search, have the search generate an alert or event, store the output in some sort of data store, and rinse and repeat with all the detections we want to build, as well as building some sort of workflow or view to investigate the alerts generated by them. But now, we've got the Splunk app for behavioral profiling. First, we build a behavioral indicator search. This is effectively a metric or KPI tracking behavior of our entities, which in our case are customers. Using the workflow, all we have to do here is point towards the data source containing our transactions, and this is the only search query we'll have to write throughout this entire building process. Select the field which identifies our entities, and use any other field selected to build a measure of behavior. In this case, we'll be calculating the hourly sum of transactions by each of our customers. Then we give the search that has been generated for us a name and schedule, select backfill to have it run immediately and confirm. Voila! A behavioral indicator search built, scheduled to run hourly and sending events to a highly efficient summary index in a matter of moments. But this is only half of the job. The next part is finding which of these hourly sums are unusual. To do that, we build an anomaly scoring rule, which uses the input of a behavioral indicator search and a specified methodology between entity-specific modes, where each entity has its own definition of normal, and entity group modes, where entities are compared with each other. For our use, we're going to be leveraging the entity group machine learning mode. We next select our behavioural indicator search, then determine the parameters for our machine learning logic. As you can see, by default, the app requires no input for threshold or distribution type to identify some anomalies, meaning we don't need to be a data science wizard to use it, but we can alter both to see how it affects the output. Once we're happy, we then score the anomalies, and this is key to ensuring that we identify the entities which are behaving most anomalously across all the implemented rules, and this can be done with static scoring on a per rule basis or proportionally to our scoring field, which here is the transaction sum. Finally, we name, save and schedule our anomaly scoring rule. Now we can combine the output of our new anomaly scoring rule with other rules to investigate the profile of our millions of customers with the entity behavioural scores dashboard. Here we can see a variety of panels covering the total posture of our platform, but most importantly we have a ranked list of entities by score across all of our anomaly rules, with context into their historic scores and which rules in particular have triggered also shown. As we can see here, Alika is the most anomalous customer, having had an unusual number of password changes, multiple physical branches visited 1 hour, and a high transaction count. So let's investigate them further by clicking on their record. Here we can now see where the entity sits percentile and ranking wise within our platform, and a breakdown of Alika's score by individual time and rule. Clicking on the score by rule pie chart drills down to show the raw events which contributed to the score in the given time window and the scoring events generated. Finally, going into those raw events takes us to the search window to investigate their behaviour and reach a verdict, meaning that we've gone from millions of transaction events to a specific anomalous customer and have found our abnormal in a sea of normal. There's a ton more to show in the Splunk app for behavioural profiling, but hopefully that has enticed you to give it a try, which you can do by downloading it from Splunkbase with the link in the description.